Welcome everyone to the new Hoover Institution workshop on using text as data in policy analysis. My name is Stephen Davis. I organized the workshop with Justin Grimmer, who's here along with me. This workshop will meet about once a month and feature applications of natural language processing, structured human readings, and machine learning methods to text as data. In terms of topical content, the focus will be on policy relevant questions in economics, history, national security, political science, and other fields. Today, we are delighted to be joined by Molly Roberts, who will kick off the workshop series as our first guest speaker. Before handing the baton to Justin, he's going to introduce Molly. Let me just say a few words about the format. We have a large number of guests, so we're not going to be able to run this, attendees, so we're not going to be able to run this in a kind of traditional seminar style. Instead, what we'll do is Molly will have about 35 minutes of prepared remarks. We will limit, you'll be able to put questions into the Q&A section at the bottom of your Zoom picture, but we're going to limit the questions during that portion to clarifying questions. So if Justin and I see that some issue comes up repeatedly, we'll interject and ask Molly to clarify. After Molly's prepared remarks, we'll go to a broader discussion. Again, please put a question in the Q&A section, and Justin and I may decide to paraphrase your question or unmute you and let you pose the question yourself. We're going to run about 75 minutes for the regular workshop. Then we're going to break for 60 seconds and come back for those who are interested in a more informal kind of how to do it discussion. So if you're new to text analysis and you want to ask some basic questions of Molly about how do you get started in text analysis, how do you do this, that's what that second little session is for, okay? All right, without further ado, let me turn it over to Justin.
Thank you, Stephen. I am thrilled to introduce Molly Roberts as our first guest speaker. She's an associate professor in the Department of Political Science and in the Halıcıoğlu Data Science Institute at the University of California, San Diego. Molly has her Ph.D. from Harvard, and she's an alum of Stanford University, where she received both a BA and an MA in 2009. Molly's research has proceeded along two, and they're often intertwined paths. On one path, Molly has provided the best understanding of how the Chinese government censors online content at scale. Molly's first book, Censored, Distraction and Diversion Inside China's Great Firewall, is an award-winning book that characterizes the strategies the CCP uses to occasionally stifle dissent and to dampen the spread of some information. Along with this book, she's provided a series of innovative articles that provide a wide-ranging and insightful view into what gets censored and when by the Chinese government and how this matters. On a second path that we're going to hear more about today, Molly's been at the forefront for text as data methods in the social sciences. She's produced a wide-ranging and path-breaking set of articles. Perhaps her best-known work in this area is the structural topic model papers, or STM, for those of you who have used the R package for topic modeling. We're thrilled to have her present work today that falls most clearly on the second path of using text as data methods. The paper, Adjusting for Confounding with Text Matching, is part of a series of papers from Molly and her co-authors that asks how to use text as data methods to make better causal inferences. So with that, without any further introduction, Molly, please take it away.
Hi, everybody, and thanks so much for having me. I'm going to share my screen. Thanks so much both to Justin and Stephen for having me. I'm really honored to talk to you today about text matching and really excited to hear your thoughts on this as well. Okay, so what I'm going to present today is a paper called Adjusting for Confounding Using Text Matching. This is joint work with Brandon Stewart, who's at Princeton, and Rich Nielsen, who's at MIT. Okay, so I'm going to motivate this with one of the applications within the paper, which is, does gender affect citations in political science? So there's a lot of discussion about the status of women in academia and also implicit bias more generally. And we build on work by Meliniak, Powers, and Walter in 2013 that argues that women are cited less than men in international relations. They use 3,000 articles published in top-tier IR journals from 1980 to 2006. And they find that women receive about 80% of citations of their male counterparts. And they use network analysis to suggest that women self-cite less than men, and also that men cite men more, and men make up a larger proportion of scholars. And so that they find that these are maybe the mechanisms, or they propose that these are the mechanisms driving this effect. So this is a really difficult study to do because there are lots of confounders, right? And in particular, women tend to write about very different topics and use different words than men in international relations, which is a subfield of political science. And so it's really difficult to figure out, based on this analysis, if the reason that they get fewer citations is the choice of topic, which then also drives citations, or perceived gender. When somebody reads an article and they see a name, then there's some sort of implicit bias that then makes, this differential in citations. So the perfect experiment in this case to identify a causal effect would be to sort of randomly assign names to journal articles and then wait for 10 years, right? And then see how many citations different people with different names accumulated over time. And this sort of audit study would, on average, because of random assignment, equalize topics across groups. So of course, this is impossible to do. And so the Meliniak et al. Solution is to rely on the TRIP coding. So TRIP is a data set that has a lot of information about scholarship and international relations. And part of this data set is that the articles are coded into many different categories. So they're coded into categories of topic and categories of approach. And then they control for these categories in the analysis of the relationship between gender and citations. And they also control for many other things that were also in the TRIP dataset, including the university attributes of the university, tenure, co-author, journal, etc. So this TRIP hand coding is a heroic effort. Took a huge amount of time, lots and lots of research assistants, teams, and a categorization of topics that then each of these individual articles were put into those topics by hand. And of course, and so this is a really amazing data set. But two problems with hand coding when we're looking at confounders is, first, the main problem is it's really expensive and time consuming. So even just coding 3,000 articles can take a long time and a lot of effort, a lot of money. And the second is that we sort of need to know what are the right categories to measure ahead of time. So we need to know which categories or which topics confound the relationship between gender and citations in order to actually know what to put them in. And then if at the end of all of the hand coding, we decided that we needed different categories, we didn't have to start at the beginning and do it all over again, right? So our goal here was to try to understand if we could measure confounding information automatically. So can we estimate the ways in which the relevant topics to condition on to estimate this effect? And we're going to do this by using automated text analysis. So the data that we use are those 3,000 journal articles from the top 12 IR journals, the same basic data that Meliniak et al. Is using from 1980 to 2006. And we merge this with the Meliniak et al. Data. So we can use the other variables within their data set, including gender, article age, tenure, et cetera. And then we compare citations for all female articles to co-ed or all male articles in while conditioning on similarities between words and topics. So we find similar articles, we control for text and non-text features, and then we estimate how gender influences citations by using this alternative automated way of estimating confounding. So text matching more generally is text as a pre-treatment confounder is actually a fairly common in many different social science applications. And the applications that we consider within our paper are in international relations are women cited less frequently than men. We also consider another application, does censorship change the behavior of social media users, where we look at how the experience of censorship influence subsequent posting rate and posting topics within for social media users. So we compare users who have been censored to have not been censored. The naive approach here would be to compare posts and posting rates after censorship between censored and uncensored users. But of course, censored and uncensored users write about very different topics than those, or censored users write about very different topics than uncensored users. That confounds this. And so we use text matching as well to condition on the text of what users wrote before censorship. So this is another example. But you can imagine just generally that text is a pre-treatment confounder. There's many different applications where this comes up. You could imagine in studies of admissions, letters of recommendations could be a confounding variable, trade treaties in IPE, congressional bills in American politics, etc. And generally text as a confounder is one of many different ways in which text can be used in causal inference generally. And Justin has done a lot of work on text as treatment. Text as outcome is another way that we could think about it. And text as the measuring of the confounder is then what we're focusing on today. But conditioning on high dimensional confounders is really hard. You can't possibly condition on every single word within a document. So one way is to say, I'm going to condition on every single word and then figure out what the effect is. You wouldn't want to match on every single word because, for example, in the international relations, you don't want to look at the same article written by two different people. That doesn't exist within the data, right? You want to look at articles that are similar enough and then compare the citation rate. So we can care about controlling for covariates also that are predictive of treatment, that are actually related to treatment. And so we want to find latent variables. We want to estimate topics or words or concepts, right, within the documents that are going to be predictive of treatment and the outcome, and therefore could be a confounder. With text, we don't always know what predicts treatment, so we want to sort of estimate that from the data. So when we started working on this, which was 5 or 6 years ago, there was really very little work on matching on high dimensional confounders. And now there's been especially in computer science, there's been a new interest in this, which is really exciting. So we don't see our approach that I'm going to present here as the end all, but maybe just the beginning of trying to think about this problem as text as a confounder and how we could best figure out ways to condition on text in order to estimate causal effects where experiments are impractical. So what I'm going to talk about today is what we're going to do is we're going to construct analogs to current methods for text. So we're going to create a text approach to propensity score matching. We're going to adapt a multinomial inverse regression, which was developed by Taddy, and we're going to apply it in a propensity score matching way. We're going to use topic models to apply to make an analog for coarse and exact matching. We're going to then identify the benefits and drawbacks of each. And then we're going to create a new method called topical inverse regression matching, or TERM, that combines both of these approaches into one. And I think uses the benefits while minimizing the drawbacks. So an outline of the talk, I'm just going to do a quick review of matching for causal inference. Then we're going to talk about text analogs to current matching methods. Then I'm going to talk about topical inverse regression matching, and then I'm going to return to the gender citation example and talk about how it could be applied in an application. So a quick review of matching. So the goal of matching is to estimate an effect with given conditional ignorability. So the idea behind this is to condition on some X so that treatment is independent of potential outcomes. And there are many approaches to doing this. There's propensity score matching, coarse and exact matching, synthetic matching, there's many different approaches to matching, basically finding observations of the treatment and control that are similar on X in order to to provide the most similarity between those two groups. So today we're going to focus on two of these strategies. First, we're going to focus on propensity score matching. So this is creating a model of treatment conditional on X and then matching on the predicted probability of treatment. And the second is to try to match on all X or coarsened version of X in this set, which is coarsened exact matching. So the idea behind this is to find units that are very similar on a coarsened version of X and match on those. Both of these strategies scale very poorly with high dimensional covariates, so we're going to have to adapt them for the text case. So propensity score matching, I'm going to sort of give a basic sort of a introduction to propensity score matching and then talk about how we could adapt this with text. So in classical propensity score approach is to fit a logistic regression of treatment on some covariates and then estimate the probability of treatment, here pi hat I. Then match units that have similar probabilities of treatment. And what the advantage of this is we've basically taken a very long vector of X, a lot of different covariates, and we've compressed that into a scalar that then we can match on. The cons is that, you know, a matching on any individual, and matching two pi's doesn't necessarily mean that those two units are very similar to each other. They mean they have similar probabilities of treatment, but they don't mean they're actually similar themselves. And so it sort of approximates full randomization more than sort of blocked randomization. And I'll talk a little bit more about that problem in the text case in a little bit. So if we wanted to use propensity score matching for text, our problem is that we have really high dimensional confounders. So when we use a bag of words approach to represent text, we take each document, so we're going to have n documents here, and we take every single word within the vocabulary of our corpus, and we make each of those individual words a variable within our data set. And we count how many times each of those words appears within each of those documents, and that's our data. And so the columns of our data set is V, the number of words in the vocabulary, which can be very, very large, you know, tens of thousands of variables, right? And so if we want to run a logistic regression on this, we can only estimate pi hat when n is much greater than v. And a lot of times this isn't the case. And so, and a lot of times, a lot of the words are actually not that useful, right? So it's also, estimating in the traditional propensity score method doesn't make a lot of sense. So one alternative approach that we talk a little bit about within the paper is using multinomial inverse regression developed by Cook and Taddy to basically estimate the relationship between each of those individual words and treatment. And so the idea behind multinomial inverse regression is basically it's an inverse regression. So it regresses X using with a multinomial on treatment, okay? So X here we are going to assume is drawn from a multinomial with parameter Q, where Q is a function of treatment. So here we're going to estimate alpha here, and we're going to estimate phi, and treatment here is with an indicator for treatment. And so this phi is going to measure the relationship between treatment and a word. So for every individual word, we're going to get an estimate of its relationship with treatment. Then Taddy shows that Z, we can create a projection Z, which is by multiplying phi and the amount of that word within a document. And that this is a sufficient reduction since that conditioning on Z makes X and T independent. So we can basically use Z to estimate this pi hat I, so we can match on Z or on pi I. So Z is sort of another sort of a proxy for the what we would be matching on in a propensity score method. Okay. So we tried this approach when we first started working on this, and I think it really does kind of reflect propensity score matching similarly. But the problem that we ran into with using just this method on its own is that texts that are equally likely to be treated are not always semantically similar. So just like I was talking about before, if I get two texts that have the same Z, the same projection, that means that they have similar relationship to treatment, with their words are similarly related to treatment, but it doesn't mean that they are similar. And this isn't a problem in expectation, but in the text case, because every model we use of text is such a simplification of the problem, we wanted to actually look at matched texts and evaluate how similar they are qualitatively to ensure that our matching method was working. In this method, we couldn't actually do that. So we liked to actually look at matches and know that they were going to be semantically similar, not just overall an expectation. And so assessing balance was something that we found to be hard here. And we thought if we could actually make the matches more similar, we could get a more efficient estimate of the effect. So a different approach that we started working on was trying to generalize coarsened exact matching to text. So the idea behind coarsened exact matching, different from propensity score matching, is instead of creating a model for treatment, instead you coarsen each variable within your data set into natural categories. And instead of matching on all of the individual, the granular data, you match on this coarsened version. So for example, if you were going to match on education, you would coarsen education from years of education to high school, elementary school, and college, and then you would match on that coarsened variable instead of the actual years of education. And what's nice about this is it bounds the imbalance on each variable within matched pairs. So I know if I match on the coarsened version of education, that matched observations are going to be either going to be both in high school or both in elementary school or both in college. So I know that they're going to be similar in some ways. The problem with using this with the high dimensional confounders is if we're trying to coarsen within variables, coarsening within each of, say, 30,000 words in a vocabulary doesn't really help us very much. So, we could say, well, we're going to coarsen, so if a word appears once, we just call it, or if it appears once or more, we call it 1. And if it doesn't appear, we call it 0. But that doesn't actually help us because we still have we still have this huge data set and we can't actually exact match on all of those individual variables. So the solution that we proposed was, well, we could topically coarsen. So instead of coarsening within variables, we could coarsen across variables. So the idea behind this is instead of matching exactly on tax and income and tariff, we sort of group all of those words into one category, call it economics, right? And then match on economics itself instead of on those individuals. So we group similar words and coarsen on them. So instead of doing this all by hand and grouping individual words into categories, we use topic models to then estimate a topic, such as LDA, and it can estimate a topical density for each document, and then you can match on that topical density instead of the raw word count. So that coarsens the word counts into topics, and then we can match on the topics. So we tried this, and the problem with using this on its own is that topics aren't always important predictors of treatment. So that means we got very topically similar matches between two documents with topically similar matches. But for example, say in the censorship case, for example, we would get matches of censored posts and uncensored posts that were very topically similar, but the way that they talked about that topic was important. And so that was so it was like above and beyond topics, there are words that are predictive of treatment that matter. Okay, so either one of these on their own wasn't actually fitting it, so we need something that combined both of these advantages. So we needed something that combines bounds and balance between documents, so the documents that are matched are semantically similar, but doesn't leave out important words that are predictive of treatment. So we created this method called topical inverse regression matching, which jointly estimates a topic density and the probability of treatment for a given document. Then we match both on that topic density and we match on the probability of treatment. And this has really nice topical bounding properties. So documents that are matched are semantically similar. And it also estimates the words associated with treatment so that within that topic specific probability, which then allows, so it allows the probability of treatment to also be similar across matched documents. So the ingredients to this is basically we use this structural topic model and with treatment as a content covariate. So there are two matrices estimated. So what I'm gonna sort of, if you may not have seen topic models before, and because I don't have time to go through all of the topic models in detail, I'm gonna sort of try to give you an intuition of what the output of a topic model is going to be, and then I'm going to show you how we sort of complicate that by including treatment, assignment, and then how we estimate the matches from there. So there are two matrices that are estimated. There's a topical prevalence matrix. So the topical prevalence matrix from a topic model is what we're going to call theta. The topical prevalence matrix is going to be for every document within your corpus. You're going to estimate the proportion of that document that falls within an individual topic. So the basic idea of a topic model is you give the model the words within your document, within your documents, and you give it a number of topics K. And then it estimates these two matrices here. It estimates the amount of each document that falls into each topic. So each of the rows of this sums to 1. It estimates how much of each document is in each topic. And it also estimates what we call a topical content matrix. So the topical content matrix says for every word in your vocabulary, each topic is going to be a probability distribution over words. So this is V, the number of words within your vocabulary, by K, the number of topics. Each topic is a probability distribution over words. So each of these columns sum to 1. So basically it's like saying, given that you're talking about a certain topic, say international relations or international political economy, then this column here is going to tell you the probabilities that you say in any individual word within that topic. And topics are often described by the words with the highest probabilities within that topic. That's often how they're described. So the model is going to sort of estimate both the topics and document assignments to those topics, document proportions in each of those topics, okay? So for the latent Dirichlet allocation, the basic idea is we create a data generating process of the words within our document using that theta matrix and that beta matrix, okay? So basically we say the theta matrix draws a topic assignment to each individual word within a document. We're using a multinomial. And then based on that topic assignment, we select the relevant column of that beta matrix, the topical column, and then and we draw a word from that probability distribution. That's how we're assuming that the documents were generated. Then we optimize this using variational Mercer-Gibbs sampling. We optimize and find that beta and that theta. So we're assuming like we're creating a model or a data generating process for the words within our document. And then we're estimating the theta matrix, the document assignments, and the beta matrix, the topics, using that model. Okay. So for the structural topic model, it's very similar to LDA, but we're going to include covariate information into the model via a prior on theta and beta. And this has been done for a lot of different work using different priors to include covariates within the model. So this allows documents to have different expected topic proportions based on observed covariates. So different theta has a prior that includes covariate information. And then also that topic prevalence matrix, it allows covariate information to be included. So for us, that's the main usefulness with text matching, is that topical content matrix, that beta matrix, is going to be basically a regression of the words on the covariate. In this case, we're going to use treatment. Okay, so we're basically going to say that the probability of seeing any individual word given a topic and a covariate for any individual document is going to be a regression, basically, of topic on topic here and covariate and a topic covariate interaction. And what this is going to do is it's going to allow us to estimate not only the topics, the probability distribution for any individual topic over all the different words, but also how a particular covariate uses words differently and how a particular covariate uses words within that topic differently. And so when that covariate is treatment, which is what it's going to be for text matching, kappa C here and kappa int which is over here, is going to give us the relationship between treatment and the words overall within the corpus, and how treated documents talk about that particular topic differently within the corpus. So we're going to use this kappa C and this kappa int to create a projection similar to multinomial inverse regression that's going to capture how much the words within each of those documents is related to treatment in sort of a propensity score way. Okay, so what we use in the structural topic model is we estimate the theta for the topical prevalence matrix. So this is the estimated proportion, topic proportion in each document, and we match on this. This is similar to that coarsened exact matching, topically coarsened exact matching. We're matching on the topics estimated. And we're also going to estimate, we're going to also match on the projection. So we're going to take that kappa C and the kappa int, and the amount of all of the words within each of the different documents. And this allows us to create a topic covariate projection of how much that document is related to treatment, how much that document is using words similarly to treated documents overall, and then also within the topic that it's assigned to for the most, like where most of its words are in there. So we take the theta matrix here, we take the projection, and then you can use any matching method you want to actually find documents that are similar between the treated and control groups. And this, we've been generally using CEM to match, but any other methods could be used. So we're basically creating a lower dimensional representation of the text with theta and the projection that captures the topics and some information about treatment. And then we're matching on those values. So of course, this is like a very complicated model to do a very difficult thing, which is try to do causal inference with observational data and observational data that includes text. So there are a lot of sort of qualifiers to using term. First is that you have to, all of your usual assumptions for doing causal inference have to hold. You have to have the relevant covariates. You have to, SUPA has to hold, so you can't have interference between units, which is often a problem within text. And we're relying on sort of a parametric method to reduce the dimensionality of the text into theta and into the projection. And so of course we have to assume that all of the relevant information about the confounders is included via the parametric method into this projection and into theta. And if that doesn't hold, then of course our causal estimates will be wrong. So we have to, there are a lot of assumptions that are sort of required for this. So once we've matched on the topic matrix and then on the projection, then this allows us to, then we can assess balance in our corpus. So once we've created our matches, we can use balance metrics to assess how similar the treated and the control units are to evaluate how good our matches are. So of course, this is a little bit difficult to do with text. So we have a whole bunch of different approaches for doing this. So first we look at the words that distinguish the treatment and the treated and the control group. So we use methods like mutual information, multinomial inverse regression, STM to estimate the words that are close to treatment. And then we see how, the words that are really associated with treatment, the differences between treatment and control in those words get reduced after matching. So we want to see if words that really distinguish between treated and control, if those reduce their differences in the matched data set as compared to the unmatched data set. The other, we look at balance on estimated topics. So we look at how much the differences in the topical proportions change after matching. In order to verify that this bag of words representation is actually working, we look at the string kernel similarity between documents within the treated and the control groups. So this is basically looking at phrase overlaps in a sense between treated and control documents and getting a measure of similarity. And so we look at this similarity measure in the unmatched corpus and then the similarity layer in the matched corpus, and we see how much more similar we get the documents after that. And then the last thing we do is we do a lot of reading. We do a lot of human comparisons. Of course, this is easier for shorter documents and harder for longer documents, but we look at matched documents and we try to sort of understand if we as qualitatively assess these documents to be similar. We can also compare them, and I'll show you this in a second, to existing human coded categories to see if they're similar amount of human coded categories. So let me return to the application here, and let me just check on my time. So, okay, I'll be done in a few minutes. So let's return to the application on gender bias in citations. So just a reminder is that Melniak, Powers, and Walters look at whether or not women get cited less than men in international relations. Of course, the main confounder here is that women write about different topics than men. So they use this trip coding to code in articles into many different categories. And we're trying to sort of do the same thing in an automated method with text matching. So we merge their data with journal articles that were written by these authors. And we look at all female authorship teams versus co-ed or all male authorship teams. And we basically use text matching to find similar articles and then see how they were cited differently. So this is just one example of in the original data set without matching. Okay, here we go. In the original data set without matching, this is looking at mutual information in the unmatched data set. So this is a metric of how much a word gives information about treated versus control. And this is all female articles minus male/co-ed articles. So words that are more used among women are over here, female authors, and words that are more used among male or co-ed authors are over here. We see that there are differences between word usage between all female authorship teams versus male and co-ed authorship teams. Some of this has to do with, you'll see this in the data, is like quantitative approaches that tend to be used more by male or co-ed authorship teams, and all female authorship teams focus on average more on topics about women, which is what we see over here. Then after we match using just topical CEM, we see that these blue are, what we want to do is we want to reduce the differences in the words between these treated and control. So we want to bring, especially those words at the top of this data set here, to the middle to reduce the differences in writing in the match data set, okay? When we just match on topics, we don't do this all the way. The blue are the ones that are reduced and the red are the ones that get worse. And we see that we get some of the way, that there's a little bit more rejection in the difference in proportion of words between female and male co-ed authorship articles. But when we match on term, those really those big differences get moved to the center because we're actually including information about treatment within our model. This is looking at the topical differences. So this is sort of a complicated plot, so I'll walk you through it. So these are each of 15 different topics that we estimated within the data set. As you can see, some of these might be familiar to you, especially those of you who are scholars of international relations. There's a war topic. This is more like a data topic. This is maybe a game theory topic. This is international trade topic, international institutions topic maybe, right? So we see some of these. These histogram here is the difference between in the unmatched data set and the difference in topics between women versus male, sorry, this should be male versus and co-ed articles. And we see basically big differences between topics. Then if you look at the projection matching here, if we just matched on the propensity score, we would actually make some of these topics quite a bit worse in differences because we wouldn't be including topical information. Even in the matched data set, we see sometimes it makes it a lot worse. But term, this filled in dot here, makes most of these topics have much fewer differences in between the treated and control groups. We also look at string kernel similarity. So here is the density of string kernel similarity between treated and control documents. And with no match, it's this sort of dotted line here. You can see that there are some similarities, but it's the density of it is around sort of 0.72. And we get the highest similarity in our term match, which is where the density is more like 0.83. So we are getting more similar documents according to string similarity as well. And we can also look at human coded differences. So what we did, this is a really hard test of the method because these are all of the different topics that those human coders put all of these articles in. And again, in the full data set are these bars, the differences between all female authored teams and male and co-ed authored teams, so the treated and control group. So we see the biggest difference here is that all female authored teams tend to have much more qualitative approaches to political science or to international relations. And then we see in the match data set, the differences are in this again, this filled in dot here. So we do see that on the most part, we are reducing the differences in even the human coded categories, which are come up with outside of reference to the literature. We do see sometimes they get worse, but this could be because these topics are not as relevant to treatment. So we're also trying to find the topics that are relevant to treatment. Although looking at these human coded matches is really important, and we could look more closely into that topic as well. So what we find, Melaniak et al. Find that women receive 80% of the citations of men. We also find this using our quantitative text matching method. This is pretty robust finding across different specifications of matching. Our final estimate, although it depends on how course you want the matches, but across all of these different courses, women receive somewhere around 65% of the citations of men. The difference, and this has also been noted in the Melaniak cases, the difference is for articles with low ranges of citations is less than those with high range of citations. So for articles with lots of citations, this difference is very big. The articles with low citations, this difference is not statistically detectable. So there, just to conclude, there's sort of lots of applications that measure pre-treatment confounders with text, and I've talked to a lot of people also that have applications like this. We propose sort of a new framework that shows that you can match on the topical density estimate, which bounds the difference between matched articles. You also match on the probability of treatment, which balances the words related to treatment. And that this we found works best in our experience, is best for overall balance. Future work, we're interested in sort of extending this to higher dimensional cases other than text. We also have an R package called text matching that implements this in R if you want to check it out. And I'm looking forward to your questions and also to the discussion.
Great. Thank you, Molly. That was super interesting. We've got a question from Stephen Hansen. So Stephen, we're going to unmute you and let you pose your question.
So hi Molly, thanks for the great talk. And I guess my question might be a little more methodological, and that's that in the STM, I've never quite understood the difference between including a covariate in the content
Yes.
Equation, which then should given the data generating process, I think that the topic distributions over words should kind of adjust to kind of line up with the covariate and the content. So anyway, the question is, if we want to kind of create a low dimensional representation of documents that we want to use to do matching, and make sure that that low dimensional representation kind of captures information about the treatment, why would you not include the treatment variable in the kind of content equation of the SDM? And what's the motivation for putting it in the kind of word probability equation? That wasn't totally clear to me.
I see, yeah. So we actually do include it in both. The estimating in the word probability equation is what drives the projection. So that's why we estimate it, we use treatment for the most part in the content, and you can include it in the prevalence as well, although you have to then match on theta estimated as if all documents were treated, because what happens is that you'll get different topic proportions for treated and control groups, even for the same text. So it's a little bit tricky. So in the overall, in the topical prevalence matrix, if you include a prior on treatment, then it's going to create predicted prevalence for each individual document with the knowledge of that treated prior. So you can estimate it in order to get topics that are related to treatment. But when you finally match, and we include this within the software, you have to estimate, you have to do the final step where you estimate it as if all documents were treated, so that similar documents or the same document with a treated and control variable actually estimated at the same topic prevalence proportion. So that's what's for topical prevalence. The reason why we do it a lot for topical content is that we can match directly on that topical prevalence matrix to get documents that have similar prevalence. But we also want to understand how words are used differently within topics for treated versus control. So by including an indicator for treatment in the topical content portion of the model, that allows us to estimate within topics what might be slight word differences. And then that allows us to then estimate the projection, which tells us, given that a document was within a topic, how much is it looking like a treated topic versus a control topic, and we can match on that, a treated version of the topic versus a controlled version of the topic. So that topical content matrix is giving us some information about the way that the document is, or the way that a topic is being talked about differently between treated and control groups. So we can estimate not only that the topic is being talked about, which is the topical prevalence, but also the way it's talking about how similar that is to treatment.
Thank you. Molly, I have two questions. One kind of a high level question, which is, how do you go about assessing balance matching in this context? I was trying to wrap my head around that. You seem to have some accumulated wisdom about what's a good way to assess balance matching in the text context. And I wonder if you could just expand on that a bit. You talked about a couple of methods. Why did you use those approaches? Why do we even need to worry about balance matching here? And how should we think about it? That's kind of the broad, vague question. The specific one is, could you say a bit more about, in your application, why you got a fairly different answer between the automated method and the human-coded, relying on human-coded data, and the extent to which women authors were less cited than male authors? What is it that the automated approach captured that was missing from the human-coded data?
Yeah, so both really good questions. So with assessing balance, this is really hard. So you have a matched data set, say, and you want to assess how similar the treated and the control units are as like an evaluation of whether or not your match worked. In text data, because it's so high dimensional, there are always going to be attributes that are different, right? And so it's hard to say when you've done enough matching to reduce those differences. And so even if you look at, some of our balance metrics, of course, we have strong similarity, I would say, in the matched data set, but there are, certainly documents that have lower similarity. It's not all one, and we don't want it to be all one, because we don't want, that would be like plagiarism, right? And in scholarship is if there were two exact the same articles, right? So of course it's impossible, it wouldn't be, right? So it would be possible that it would be the same. But the question is like, is it the same enough? And so looking at, especially at differences between treated and control on topics and on words, and then, looking at the human coded categories, but also in the censorship case, we just had, teams sort of assess, look at match documents and say, by your evaluation, what, was one more likely to be censored or not, right? Is that like, that could be one way within a human evaluation that you would try to evaluate this. So like looking at pairs and saying, do I see that that difference as that difference between the treatment and control as being relevant to treatment? That's sort of what you want to be looking at within the human comparison, but it's really difficult, of course. So looking across a lot of different matches can be useful to sort of assessing robustness as well. And we do that a lot within the appendix of our article, look across a lot of different matches. I think so the second case is, why did we get a different answer? So one of the things about matching is you're sort of changing the population that you're studying, because you're only looking at the instances that are similar enough to be considered. And so one thing that it could be, so of course we're then only looking at this match data set. These are articles that are similar enough, where there was a match that was similar enough to be considered. So it could be that the differences are actually coming from the things that were excluded. So in the topics where there weren't good matches, that those were sort of like create the difference between the Melanie Eck et al. And our estimate.
But that seems like something easy to evaluate directly by just taking the subset of their analysis, their data that meets your matching criteria, and recalculating their answer.
Yes, yeah, exactly. That we could do directly. That's right. Yeah.
I sort of have a question, just sort of thinking through, the normal comparisons we might make to matching estimators. We might think that there's a sort of regression adjustment strategy. And so I guess the analogous strategy here would be some strategy where I would try to, run some regression where I would have something like the bag of words representation is like a bunch of covariates. And then I would try to either regularize that or estimate some like regression with a factor model in it. And I'm curious if you all have made that comparison and why there's a reason you went to matching instead of the regression adjustment, or is there something faulty in the regression adjustment strategy that doesn't get it off the ground?
Yeah, so that's a great question. So one of the issues in the regression, so you could estimate with this by regression steps. So say you take your bag of words, you have all of those V variables. You could run like a lasso where you're just regularizing and dropping out words that aren't useful, and then you would estimate the effect conditioned on those words that are considered relevant. And actually have done this, and just as a plug, like we do this, Justin and Brandon and I do this in our book that's coming out on Texas data. So we use a regression adjustment strategy first and look at the differences between on the words. And I think that's one way to do it. And actually you get a very similar answer. Again, like what we liked about this is that we could actually find pairs of matched and unmatched documents and then like assess them qualitatively. And I'm not, I think that there's value in that, whereas like you can't do that really in the regression adjustment strategy. So I think there can be value in that. And I think there's also the sort of more general argument of matching as, removing the variables or the data that's sort of doesn't have a comparable element within either the treated or control group can be useful for reducing model. Like you can make that argument as well, reducing model dependence or making inference. Yeah.
I've got kind of another sort of a groping question, but there's as someone who's very much a beginner in trying to understand and use these methods.
Yeah.
There seems to me to be, there's lots of assumptions, distributional assumptions, choices that are made, and so on, and kind of raises the question of how well are these methods working in practice. You've talked today about a comparison to a human coded method, and I don't know this context. The human coded outcome may or may not be a good benchmark against which to evaluate the performance of your models in this context. I just don't have the domain expertise to make that judgment. But that leads to the question, are there settings that you can think of where a human coding approach has been taken to a question and we're quite confident in the end? It's a real world application, but we're actually confident that the human coded answer is right. And then we want to use that as the benchmark against which to evaluate the performance of a whole bunch of different choices you can make as you implement this method. So I'm basically groping if are there such cases that come to mind, and if someone out there is listening to this and wants to kind of put your approach here through the ringer and see how well it performs, where would you point them to go?
So I think this is a great question, and like there's like it's like the Lalonde data with the matching, right, where everybody sort of compares their matching estimate to the Lalonde data. And to be honest, I don't know of a good like benchmark data set in some sense in text, but I've been thinking about how to create one. So like you can imagine that you just generate, you could like introduce confounding in an experiment where you introduce it only for half of, like in an online experiment, for example, where you introduce it only for like half of your data, where you don't introduce it for the other half. So you like randomize the confounding information, like you like randomize, you get treatment assignment based, and then you could see if you could actually recover your estimates with that in that experiment. I think that would be pretty cool. I have some ideas on how that could, like, I think creating benchmark data sets for causal inference with high dimensional confounders and for causal inference generally is useful, but of course, like every application is also different. So what might work in one application might not work in another. Like it might pick up the relevant information in the experiment that I designed online that it wouldn't in like JSTOR articles. But it could be a useful thing to look at. Yeah, it's a really good question.
But please, we've got scope for other questions here. If folks don't be shy. So just here we've got a question from Amirali Babani. First, please tell me the correct pronunciation of your name, and then go ahead with your question.
Sure. My name is Amir Babahani. I just go by Amir, but it's Amir Ali. So, I mean, I've just written the text. I tend to be kind of epistemological in my understanding of things. So I'd rather just let the text speak for itself.
Okay, you want to go ahead and read it, or you want me to read it?
Sure. Well, I could read it. So I said, this is brilliant stuff. You could use this sort of model to find implicit bias when evaluating college applications for program entry essays. Do you think you could find an organic causal inference that would show a college's or a university's method as discriminatory?
Oh, that's an interesting question. So, so the basic idea would be treatment, like a protected trait, and then the confounder would be like a college essay, maybe. Yeah, so I think you'd kind of have to think about the causal, like the causal diagram, like what comes before treatment, what comes after treatment. This is something that we also struggled with this gender citation. Like I think the easiest way to think about it is in like an audit study as like a thought experiment, right? If you had a different name, would there be a different, on an article, for example, in our case, would there be a different sort of citation rate, right? I think so you could think about it in that way if there was sort of a different name. would then that have a different acceptance rate. And if the essay or letter of recommendation or something was like confounding that, then you might be able to account for confounding with the essay. But I have to think through sort of the causal diagram to try to figure out exactly what you would want to condition on and what is before versus after treatment and that kind of thing. But I think there could definitely be applications in that area.
Thank you. I don't know if you could still hear me.
Yeah.
Yeah, I was, I'm more interested in the behavioral economics and the neuroeconomic factors that go into, how we push people through college. So
Yeah,
it was very interesting stuff. Thank you for taking my question.
thanks so much, Amir.
Yes, thanks for the question. Okay, we've got a question from Chenji Xu. Can we unmute Chenji and go ahead and pose your question?
Hi, thanks for your presentation, Molly. So I'm an economist, and I often work with historical data, and am trying to venture into historical text analysis, and am wondering how to think about the different contexts that these the historical documents would come from. So very simply, the difference in the way they use words, or even different syntax or type or vocabulary, and whether it's possible to, or whether the issues of mixing corpuses like that would come more from like adding noise, or whether you think this would also introduce bias in trying to group topics and do the sort of analysis that you've presented here.
So the challenge here is that you're grouping sort of corpuses that are sort of different corpuses together.
Yes, yes.
Yeah. So I think that can be really challenging, especially because the way in which the topics, or for example, in a topical analysis, the way in which the topics are estimated then could reflect the medium, right, rather than the actual content. And so I do think actually something similar to text matching could be really helpful. So we wrote this paper in political analysis about text analysis for comparative politics, which I think maybe has some analogies where we're looking at trying to merge corpuses with different languages. And one of the problems of doing this, of course, is even when you like translate all of the words, there are some like mistranslations that are systematic, that mean that that can kind of drive results that are differently. So we actually end up using the content covariate within the structural topic model to account for like these mistranslations, and which allows the topics to merge with each other. And it could be that you could use the content covariate for like the different modes, the different corpuses of your text, to then sort of merge, to allow the topics to merge with each other. And then you could do a human evaluation of documents that are supposed to be similar and different between each of those. Actually, a lot of Justin's work has some good sort of like experiments for human evaluation, where you can like say, are these similar, are these similar, are these different, are these similar, are these different? And then you can like try to figure out if you still are getting differences just based on medium rather than based on actual content. So that might be like that as like a validation. So like that might be one way you could kind of merge two corpuses together, and then like verify that it's actually working. But sounds, I mean, I think it's a really hard problem. I'm not sure it's completely solved. So maybe you'll push us forward in that direction. I think using historical data is really utilized in this area.
I have a follow-up question, actually, if that's okay. You mentioned these mistranslations. How did you guys figure out that that was an issue? Like that was just very obvious from looking at the data, or from human intervention? Or?
Yeah. So if you put two corpuses of different language texts with different languages together and you run a topic model, you'll get a set of topics in one language and you'll get a set of topics in another because there's no overlap between the words.
Mm.
So then if you do automated translation of one of those into the other language, or them both into a third language, say, so they have the same, then when you run the topic model, we realized we were still getting different topics for different languages. And if you we looked inside of, even though they were translated into the same language, but when we started looking inside, we started realizing that alcohol would be translated to spirits in one language, but would be translated to alcohol from another language, that's just one example, but lots of different things like that. So, and those systematic translations then sort of drove differences between topics. And so so that's where we started running into some issues. I think there might be similar differences between medium, but
Right.
have to sort of think that through. And I think when you started exploring and reading the text, those things would sort of come up.
There's not another question. I'll just jump in here with an observation that comes out of my own work, which it's not doing causal inference for the most part. It's more of a basic measurement effort and trying to measure economic uncertainty initially using newspaper articles. And there the issue was, well, is newspaper text really a very useful or authoritative source as a tool for quantifying the extent of economic uncertainty in the economy? Mm-hmm. So one thing, and we did this not using topic models, but just expert curated dictionaries to classify newspaper articles that met certain criteria, that they were talking about economic uncertainty, into categories, topics you can think of them as. And one way we tried to evaluate that was go to more authoritative text sources that were limited in other ways relative to newspapers and see whether they told a similar story. I think more later, independent work by Tarek Hassan and others looked at the transcripts of corporate earnings conference calls. Very different text source, and using somewhat different methods, more natural language processing methods, to do similar quantification and classification exercises. And happily for us and for him, the nature of the answers came out to be fairly, show a lot of similarities in terms of the movements in economic uncertainty over time and the underlying sources of that economic uncertainty according to these text sources. So I think the payoff to using multiple text sources was really kind of a cross-validation one. And at least in the context of trying to quantify nebulous concepts, which I think of as economic uncertainty as a concept that plays in a central role in many economic models, but is hard to quantify directly outside, say, VIX-like measures for financial markets. It's very useful to try to consult multiple text corpuses and see whether they're telling you a similar story. So Chenji, I think there's actually advantages in that respect, kind of a cross-validation sense, in doing historical analyses and trying to integrate over a variety of text sources when you can.
Yeah, it certainly means that something, if a measure sort of generalizes to a different corpus, that means it's robust in a way that you wouldn't, that you can use it more generally than just whatever corpus it was developed on. So I think that's that's a really neat kind of validation exercise.
So I have a sort of another how-to question and sort of thinking about how to situate this into the literature. And Molly, I was hoping you could say a bit about word embeddings. So I believe this is more of the Veach approach, uses word embeddings to do this. What do you view as the sort of trade-offs there? How to think about topic models within this sort of broad scope of different approaches here? Is word embedding better in some situations than topic modeling, or?
So I think it's sort of hard to say. what I'd like to do is do some more comparison. I haven't had the chance to do this yet, but sort of like apply the Veek approach and our approach, and then also try to do some comparisons to see, like, in terms of, like how on a benchmark data set, ideally, right, to try to kind of get an idea of which one, when one works better, when the other works better. I think the advantage of the word embeddings approach is that you're going to be able to leverage like a much sort of larger sort of vocabulary and all the relationships between words within that vocabulary to do the estimation. But I think, it's difficult in their approach to actually, again, I maybe am too wedded to the pairs of articles, but like actually, this is the very social science, I guess, perspective, is just actually able to look at those pairs and see if they're similar is, like, I think a really useful exercise. But you definitely don't want to, not use a useful approach because you can't look at pairs, right? So, so I think that there's more work to be done to try to evaluate like the benefits and drawbacks of each of these different approaches. And probably the topic model one is going to work better, and the term approach is going to work better when the confounding variable is likely to be topical. So in some situations, the confounding is maybe less likely to be topical than others. And I think in the gender citations NIR is one example of where we might expect it to be very topical. But in other cases, we might not expect topics. We might expect sentiment or something else to matter more. And so then maybe term would be less useful in that case.
Great. I want to, we're getting near the end of our time for our regular session, but I want to do two things before we close this off. First, I want to show a picture of the book that maybe you see it in mirror writing that that Justin mentioned at the outset. This is Molly's book, Censored, Distraction and Diversion Inside China's Great Firewall. I'm about halfway through the book. It's super interesting. So if you want to see kind of an extended discussion, and I would say this is less compressed than Molly's presentation today, so you can read it and get an introduction to the literature on censorship and propaganda, but also see Molly's contributions to the area. It's super interesting. I recommend it highly. And then Molly, we're gonna break shortly and see if anybody wants to stick around for more basic how-to questions. But before we do that, speak to your audience, some of whom are new to this area. Where should you go to get started, both in terms of understanding concepts and methods, and also just finding code chunks that I can work with and expand? I mean, we do want to make this a vehicle for helping people get into this field. So perhaps you could say a few words of that in closing.
Yeah, for sure. Well, thanks for highlighting the book. I think that that's really nice of you. In order, for people who are kind of interested in getting started on this, I always point people to the Grimmer-Stewart 2013 political analysis article, which is sort of like an overview of text as data methods. And, I think that there are a lot of really useful also code introductions online, both like Quantita, Ken Benoit's package, also there's some new tidy text, also our packages and books that you could check out. Brandon, Justin, and I are writing a book right now that'll be coming out soon on text as data, but this is more of like a research design book. So like, how do you think about using text for different tasks? So this is less of a code-based book, more of like a research design. How do you think about when you get a text data set and you want to measure something, how would you approach that? When you don't know what you want to measure, but you just want to explore it, how would you approach that? When you want to do causal inference, how would you approach that? When you want to do prediction, how do you approach that? How do you think of these different trade-offs and sort of pitfalls? So I think that hopefully that will be a good resource for all of you, but you can tell us. So I think there are a lot of really great yeah, introductions and sources to get started with. And yeah.
Okay, well, Justin, any last words?
Just thank you to Molly for a great presentation, a real sort of tour de force of text methods and causal inference, and a very interesting application, which we could have, of course, spent much more time on. It's fascinating.
Yep. Great. All right. Thank you so much. This ends the recorded segment of the session.